Thank you. So, oh, she's not here today, actually. Can I give it up to you? Thank you, honey. All right, friends. So the last few days that we have been together, which was not yesterday, but in the days leading up to that, we have talked about some optical phenomena that are pretty important. We talked about refraction, the bending of light. We talked about diffraction, or excuse me, not diffraction, I'm sorry, dispersion, the separation of light into different colors. And we talked about total internal reflection. And the three of those come together in perhaps my favorite optical phenomenon that one can see. The picture that I had up last time, I think some of you were giving me a hard time that it looked fake. This is a picture that I took of a double rainbow, okay? This was my camera. I don't know why it's at a funny angle, but it is because that's just how the world is. This is just another light pole there. It just looks really funny in there. But this is a double rainbow that I saw. It was so exciting. Proof of that is that it's not a very great picture of me and my kid, but so there we are with the so it real I was there. I promise. Not photoshopped in or whatever. Double rainbow. It's pretty cool. It's all physics. It's all light. Okay. We are going to talk about where they come from, how they happen. You kind of brainstormed a little bit, but we're just going to jump in because we don't have tons of time. I would like you to draw a big circle somewhere in the middle of your paper. It doesn't have to be in the middle, but somewhere around this, at least, 5 lines big if you're using lined paper. That big circle represents a raindrop. Raindrops are made of what? Water. And outside the water, what surrounds that raindrop?
Air.
Yeah, these are not like wild and tricky questions, friends. So one of the things that you must have in order to have a rainbow is water droplets. Water droplets in the air. You could also have water droplets like from a hose, right? If you've ever been with a really nice fine mist spraying the garden or spraying your little brother or whatever, right? You can see rainbows in that too. Same principle, okay? The ones I'm going to talk about are the ones that we see in the sky just because I think it's a little bit more ubiquitous, but it's the same process. So air and water. And what's the third thing that you have to have in order to have a rainbow? Got to have light, right? Got to have light. The light that we're talking about usually comes from the sun, okay? So this is the sunlight. So there's another picture that I'm going to show you in just a second that's got a big sun up here. I just didn't want to freak you out with tons of picture things. So there's your sun. The white light is coming from the sun, and white light includes what colors?
All the colors.
All of the colors, right? It's all mixed into one. And so we're going to look at this light. Now, when this light hits the raindrop, we're going to go ahead and draw kind of a parallel or a surface line, and then I'm going to draw my normal. Okay. So that we can look at this. Which one is more optically dense?
Water.
Air or
water?
Water. When light goes from something less optically dense to something more optically dense, which way is it going to bend? Toward or away from the normal? Toward the normal, right? Because it's slowing down. So it's going to bend toward the normal, which is exactly what we see here. Here's our angle of incidence. Here are our angles of refraction. This happens because of, remember what it's called?
Dispersion.
So we're just going to kind of take this one little piece at a time here. This part right here, that is the phenomenon of refraction. This right here, that is the phenomenon of dispersion. Okay. So you got that white light from the sun. It comes in and it starts to split up into all of the colors. Red, orange, yellow, green, blue, indigo, violet. Indigo, maybe not, depending on who you want to talk to. Okay. But regardless, that light is going to come over to here. And now this is key. because this raindrop is at such a location and the light is coming in at such an angle that when the light hits the back of the raindrop, remember, because going from water into air, it would bend away from the normal. You remember this from a couple days ago, right? The light's going to bend away from the normal, but the angle it's coming in at is big enough that bending away from the normal would be back in water. And so what happens at this place right back here? What happens there? What's that called? Reflection. And not just reflection, but what kind of reflection? There was a name for it. Do you remember from 2 days ago? Last time I saw you. Look back in your notes if you don't remember. What's it called? Close. Total's the first word. Internal reflection. Total internal reflection is what happens back there. So the game is that the light comes in, all is one, it bends, it spreads out, it reflects off the back, and so it stays in the water droplet until it exits here, and now the angle that it's coming in at is small enough that it's just going to bend out. So if you look at any one of these little spaces right here, right, if you look at the normal line, it's bending now away from the normal. So here's my angle in, here's my angle out. It's bending away from the normal because we're going into air from water. Okay? That's how we get all of those colors to be broken up into pieces. So we've got refraction again right here, and you've got lots and lots of dispersion right here. Okay? Actually going to erase that green because I want you to notice the order of those colors. If I went into my daughter's kindergarten class and I asked all of her kindergarten classmates to draw a picture of a rainbow, they could do that, right? Sure. If they were going to draw a picture of a rainbow, what color goes on top? Red, of course it does. But what do you see over here?
It's on the bottom.
The red is on the bottom. Does that mean that my daughter and all of her classmates are wrong?
No.
No. They've seen rainbows. Oh my gosh, and the red is on top. If we go back to the picture that we saw before, right, the picture of the rainbow that I saw, red is on top. It for sure is. Here it is. Red, orange, yellow, da, 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 right? It's on top. So my question then is, what's up with that? When you look at a rainbow, are you standing really close to the water droplet?
No.
No, it's a long way away, right? Long way away. Look at these light rays. Are they going to stay right next to each other as they travel? What are they going to do? They're going to spread out. Does that make sense? They're going to spread out. And so the red light is going to go one way and the violet light's going to go another way. They're not both going to hit your eye. You can't get a rainbow that you see from just one raindrop. It takes a lot of raindrops in order to get a rainbow, in order to actually be able to see it and for your eyes to be able to process that that's what you see. So what really happens is that you've got sunlight hitting 2 raindrops, or 3, or 12, or a million. And the light comes in and does the same thing on the top raindrop as the bottom raindrop. But the light from this top raindrop, the red light is going to go in the same direction as this violet light is here. And if we add this person, okay, over to the side here, he's going to see the red from this raindrop and the violet from this raindrop. You with me there? Okay. Obviously not drawn to scale. Like, to be very clear, it's not. But it shows you nicely how the red from this top raindrop and the violet from this raindrop then would come to his eye and make it look like a nice rainbow. Okay?
Does that mean that everybody sees like a rainbow from different raindrops?
Say that really loud.
Does that mean that everybody sees the same rainbow from different raindrops?
Yes. Did you guys hear what she said? I'll say it one more time. She says, does that mean that everybody sees a different, did you say different rainbow from the same raindrops?
Different raindrops.
Different raindrops. Yeah. So if and I like to pick on Alec, not for any reason except that you're a lot taller than I am, right? So if you imagine Alec and I are standing there, we're like, oh, look at that pretty rainbow. The rainbow that Alec is looking at, the rainbow that I'm looking at, are not the same rainbow. The raindrop that's providing his eye with red light, all of the light from that raindrop is going over my head. Like literally. Like it's going, because it's come stand here just so we can like imagine this, right? Like he's not the same. Whoa, that was exciting. So any light that's coming into his eye, like if you imagine that, it's going right over my head. You with me there? Okay? The purple light that I'm getting coming into from here, right, is gonna like hit him in the belly. Okay? So we see different rainbows. Okay? Yeah, thank you for being tall. And we appreciate the height of everybody, right? But like it's just a nice, like you can definitely see it, right? Now here's the other thing though, is that if you're standing here and staring at a rainbow, the raindrop that is providing you with that red light and that orange light, if I take a step this way, different raindrops. You with me? If I take another step, it's just every single time it's different because the light, it's just the light that's coming there and it just happens. It exists whether you're there to see it or not, I guess is what I'm trying to say. Okay? Yeah?
We're kind of confused because if you're just standing there and you're looking at a rainbow, they don't just like stop. The raindrops, they don't just like stop.
What do you mean they don't stop?
They fall.
Oh, I see what you're saying. Yes. Okay. I thought you meant like, I'm going to reflect light. I'm not. Okay, but you're saying that they're falling?
Yeah.
Agree. So again, is it going to be one raindrop or is it going to be millions of raindrops, right? That just happen to, at that moment, this one, because it's just a picture at a moment, right? These raindrops can be falling and it just happens when he's looking for that moment that raindrop is refracting red light that's hitting you. But maybe later it's going to refract purple light.
What if it's not raining?
It doesn't have to be raining on me. Where does it have to be raining?
Away.
Over there. Now, quick question, because we haven't said this yet. Where's the light? Where's the sun? Do I look towards the sun to see the rainbow?
No.
Look at where he is relative to the sun. Is his back to it or his front to it?
Back.
His back. So if you want to see a rainbow, and it's not every moment of every day that it would happen, right? But there has to be very small drops of rain. It's a good question. I appreciate that you're asking it. There have to be small drops of rain at the right angle because it's always going to be at the right angle. Not a right angle, but at the correct angle, okay? Such that the light comes in, it refracts, it total internally reflects, and then it comes back and hits you in the eye. Yeah. Is that so far so good? Okay. I feel like I had one other thing to say. But I don't know what the one other thing was, so if it comes to me, I'll let you know. But we'll go here and then here. Go ahead.
So could purple ever be on top?
Well, that's a great question. Hold on to that question for just a second. Let me see what this one is, and then I'll come back to that.
So what causes it to be an arc instead of
So it has to do with the angle of the sunlight coming in and the angle of it refracting off of the back of the raindrop such that you can actually see it. Because all of that light has to come to you, which means it all has to come from, like if we kind of work backwards, right? From raindrops that are in a space such that this here, so like if there was another raindrop over here, like directly over, then it's going to come and hit his friend that's standing out here. Does that make sense? So if you think about it in terms of, it's kind of like a circle, right? The geometry of it works such that it makes an arc. And actually, if the ground wasn't there, it would be a whole circle. Yeah. I've heard of it. I've never seen a picture of it, but I've heard about people actually seeing rainbows from like airplanes or from above, and you can actually see the entire thing, the entire circle. The day that I saw that other rainbow, the double rainbow when I was in Des Moines. It was really interesting because it was late in the afternoon, and we were driving. We happened to be driving from Des Moines to Iowa City, and so we were driving because the sun's going down that way, right? So we're driving, and we're just chasing the rainbow, if you will. But it was really cool because the rainbow was really, really distinct for a long time, and then it started kind of going away at the edges. What is that? Then I realized that the sun was starting to set, and so there wasn't as much direct light, and so it just goes. Right? Because you have to have that direct sunlight. So you have to have sunlight and rain, the right amount of rain in the right part of the atmosphere. I'm going to come back to your purple thing in just a second, but you wanted to ask one more question.
So I understand that you see the bottom of that one and top of that one.
Yeah.
How do the other colors?
So this is not drawn to scale, and there are lots and lots and lots of raindrops in the middle. So there's another raindrop right here that's going to give him orange, and then another one that's going to give him yellow, et cetera, et cetera, et cetera. Does that answer your question? I'm trying to make sure I'm okay. Yeah. This is just the two extremes, right? If you got one, you got the other, you can put all the rest in the middle. Yeah. All right. Yeah.
So why is it that you see 3 rainbows?
3 rainbows? What do you mean 3?
Because I saw 3 rainbows once when we were at Disney, and it was really rainy and foggy. And
I think that Disney paid to make that happen. No, I don't know. Three arcs together.
They were inside of each other.
Okay, so double rainbows are a thing.
Yeah, but it kind of looks like 3. I don't know if that was just
So
the angle or something, or it was starting to fade.
So that's probably what it was. So this is the primary rainbow. The primary rainbow was from red to purple or red to violet or whatever you want to call it. Okay. The secondary rainbow is going to answer Jacob's question in just a second. There is such thing as a tertiary rainbow, but the way that the angles work out, the tertiary rainbow actually appears over the sun. It's weird. So they're very, very rare. And so my guess is that what you were saying was just that it was fading and it was kind of getting a little bit funky, or that Disney paid somebody lots of money to make it look right. Only at Disney can we da-da-da-da-da. I mean, I don't know. I did hear from a friend of mine who knew somebody who used to work there that they all of their shows, it's money is not an object, just make it. Yeah. So maybe that's what it was. I don't know. That's awesome though. All right. So let's talk about this double rainbow thing, right? So a couple of interesting things. This is not a picture that I took, but it's a nice, holy bananas, it's all right there picture. So you got red, orange, yellow, green, blue, indigo, violet on that primary rainbow. What do you notice about the secondary rainbow? Can you see anything?
Upside down.
It's upside down. Tell me about its brightness. It's much less bright, right? So those are the two things that we want to know, is that it's going to be flipped and it's going to be less bright. And the reason for that is that if we look at the light that's happening here, so let's just go back to the primary rainbow just for a second so you remember what's going on. So light comes in, refraction and dispersion, total internal reflection, refraction and dispersion, boom, right? Purple on the top, red on the bottom, but then that's how it hits your eye. That's what happens with the primary rainbow. The secondary, they call it the double, I call it a secondary bow, okay? It's coming in at a different angle. So it's light that's hitting raindrops at a different angle, which means that they're up higher in the sky. Because if you look at this light is coming down and it's hitting the bottom, lower in the raindrop than this one. Does that make sense? Okay, so that light is coming in up higher. It comes in, refraction and dispersion, total internal reflection. But then what happens up here? What's this? Not trying to trick you guys. What happened here? Total internal reflection. That's what happened right here. Is that right? What happens right here? Same. Okay. The reason that the double ray or the secondary bow is less bright is because it does 2 reflections. At any time when you reflect, you're going to lose a little bit of light. So it's going to change the intensity of the light. And then once it bounces off over here, notice what's on top? Red. What's on the bottom? Purple. But then again, when we're coming to one's eye, it's not all from the same light or the same raindrop. So you got the purple on the top and the red on the bottom. Okay. So the things, if I were you, that I would write down about a secondary rainbow is that the colors are inverted. It is less bright. And both of these things are a result of two total internal reflections, not just one. Okay? Two total internal reflections, not just one, cause the colors to be inverted and the light to be less bright. It will also always be on the top because the light is coming from higher up or the raindrops are higher up to get that right, the correct angle. Yeah.
So in the winter when they're like, sometimes they show pictures on the news because of the sundogs.
So it's similar. It's a little different. I'll tell you guys about that next week because I don't want to confuse the two. Does that make sense? But we will certainly talk about sundogs because they're pretty awesome as well. Yeah. What are the three optical phenomena that make a rainbow? The three things that happen as the light comes in and goes out. What is it? Dispersion, refraction. Okay. Make sure you know those three. Make sure you know those three. Just saying. Yeah. Total internal reflection. Yep. Okay. If for whatever reason you were not here last time, make sure you watch the video from last time because there was a lot of physics that we talked about last time and I don't want you to miss out on that. All right. Okay. We got more to do still. Can we move on? Okay. We've said this a bunch of times. I've had this same page up a bunch, but I want to make sure that this makes sense to you. When light enters a new medium, it bends. How far does it bend? It depends on the wavelength of light. This is dispersion. This is dispersion. If you haven't written this set of stuff down, you probably should. It depends on the angle of incidence. Okay? We're going to talk a little bit more about that today, but we did give an example of that last time. That was the total internal reflection. When light is in a more optically dense medium, and I'm going to say light is in it and gets trapped. Watch the video if you don't know what I'm talking about. Okay. The third thing that it depends on is the material or the medium, and that's what we're going to talk about next. Okay. So I'm going to click ahead here. Actually, I'm going to make myself a new page and say, we've been using the term optical density a whole lot. But we haven't really talked about how it's quantified. That's what we're going to talk about right now. So optical density is quantified by what we call the index of refraction. The index of refraction is marked with the letter N. It's a little n. An index of refraction is defined as the speed of light in a vacuum, that's C, divided by the speed of light in a medium. Okay. Who remembers what the speed of light in a vacuum is? Can you remember that number? We got that in their head? Or you can look it up. What was it? 3 times 10 to the 8th meters per second. That is on your equation sheet, so it's not something you have to have memorized. It's just one of those that kind of gets stuck sometimes in your brain. Tell me about the speed of light in some medium. Something other than a vacuum. Is it going to be faster or slower? It's going to be slower. So the V value will always be, not greater than, wrote that backwards, less than 3 times 10 to the 8th meters per second. If C is always 3 times 10 to the 8th and V is always less than 3 times 10 to the 8th, what can you tell me about the value of N? I'll make it a fill in the blank statement. N will always be blank than 1. Will always be, what was that? Greater than 1. Yes. The index of refraction will always be, we'll say greater than or equal to, because if it's in a vacuum, then it would just be 1. Greater than or equal to 1. Okay? The higher the N value, or the higher the index of refraction, what does that tell us about the speed of light in that medium? Is it going faster or is it going slower? The higher the N value, what is it? You're right. The slower, right? The bigger this value is, that means the smaller this value is. Okay? That's the speed. The V is going to be slower. The higher the N, the slower light moves in that medium. Okay? So you can figure out the index of refraction of any material, translucent material, so things that light can actually travel through experimentally. You can measure it. And in fact, we're going to do that in our lab next week. Okay? But I'm not going to expect that you memorize indices of refraction. I don't feel like that's a fair task or even a valuable task for your experience. You have a chart that looks something like this in your book, okay? But this just shows some indices of refraction of different kinds of materials. So take a look at this and see if you can see any patterns or any things that look interesting. You notice anything interesting? What's that? You can see through all of them, which makes sense because we want to be able to send light through them, right? Yeah. The really, really high ones, what do you notice about those kinds of materials? What are these? Solid, liquid, gas?
Solid.
They're solid, and they're all pretty dense, right? Solids are going to be more dense. And then the ones way up here at the top, at least those first two, those are both gases, right? So I said that index of refraction and optical density often have things kind of relate to actual density, but they're not exactly the same thing, okay? And I want to show you this really quickly so that you can see this and prove to yourself that optical density is not quite the same. So I got a beaker. This is, I just stole it from Hughes, right? It's just like the regular glassware beakers. They're made of Pyrex. You guys have heard of Pyrex before, right? You got Pyrex stuff at home, maybe like those big measuring cups, the big glass ones, or maybe some like glass storage dishes or something like that. That's what this is. And then inside of here is just oil. It's just corn oil, or vegetable oil. I've got it right here, okay? So I'm going to show you this. Maybe I'll show it to you on the, yeah, hold on just a second. Let me pause this. And you'll be able to see it. The reason that you see edges is because the light bends, right? When light bends around things, you see edges. That's the whole game. That's how your eyes work. The index of refraction of oil and the index of refraction of glass, of this kind of Pyrex glass, is exactly the same. And if it's exactly the same, that means that light moves the same speed. And if light moves the same speed, that means that light's not going to bend. And so instead of like at the top, where we're going from air to glass to air to glass to air to glass to da-da-da-da-da, it's bending, 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 bending. I can see the edges. But when it goes through down here to the light, this is weird because it's solid and liquid, but to the light, it goes in, it says, oh, I got to slow down, right? because I'm in this glass and the glass tells me I have to go slower, and then it just goes at the same speed. It marches through the glass and through the oil and through the glass and through the oil, through the glass and through the oil, through the glass at the same speed. And then it slows down at the other end. It's weird, you guys. It is super strange. And it's awesome. So the moral of that story is just that the index of refraction of two materials can be the same even if their densities are very different. The density of oil and the density of glass are not the same. You agree? Right? Okay. Optical densities are not always indicative of densities. There's actually two things right here, glycerin and quartz glass, that have similar properties. Glycerin is what they use to make soap. Okay. Lots of dish soaps and things like that have glycerin in them. And quartz glass is obviously glass. Same deal. So if I got glycerin and quartz glass, it would do the same thing. Okay. So that's just kind of interesting and a piece to know about index of refraction. So now our game, and this is the thing we have to get written down today before you go, is that we can take this stuff, this index of refraction business, and we can take the angle in, angle out. Is it going to bend toward or away from the normal stuff? And we can put them together into a quantitative formula that tells us how much light is going to bend. It is known from its, I don't know, the guy who wrote it down. I don't know anything about this guy, but his last name was Snell. That's the one thing I do know. And this rule is called Snell's law. Again, it is the equation that quantitatively describes how much light bends when it enters a new medium. Okay. So I'm going to tell you this equation. We might play with it a little tiny bit, and then tomorrow you'll get a good chance to get your hands dirty with it and really understand how it works. So Snell's law is pretty straightforward, but some of my grumbly trig friends over here are going to be mad because it does have a trig function in it. If you want to see where it comes from, if you want to know all the nitty gritty, let me know and I can show you because it's really kind of cool. But for today, we're just going to write it down. It starts off with an N. Remember, N is index of refraction, and this is N sub I for the index of refraction in the initial medium or the incident medium, okay? So it's the index of refraction in the first medium. We're going to take that value and we multiply it by the sine of theta I. You've seen theta I before. Theta I is the angle of incidence. We're not going to draw triangles and do, opposite and hypotenuse and stuff like that. We're just going to go with, it's the trig function. Let's run with it. It's on our calculator. Okay. Again, if you want to see where it comes from, just let me know. Equals NR. So this is the index of refraction in the second medium times sine theta R. This is the angle of refraction. So this is the angle in, this is the angle out. Okay. The game when you're studying these or when you're doing these problems is you're going to follow the guess method. Givens, unknown, equation, write out your solution and solve it. Just the same as we've always done. Okay? I am going to give you right now, so that the sub does not have to tomorrow, some problems. I will record, before I go today, solutions for these problems so that you know how to do them. You can watch this tomorrow during class. Can you pass those back? Okay? Or you can watch them tonight. Tomorrow in class, you will need to work on your homework. You are not, guys, listen, I want to make sure you hear this. You will not be allowed to work on other things until you can show him that you've done all of your homework from this section. Okay? I want to make sure you understand this so that you can master it. Have an awesome weekend. I will see you on Monday. Be well, friends.
How are you?